Section: Introduction. In this section, we discuss the diffusion method, which has become the standard for generating large-scale images and videos. A key area of research is reducing the cost of generation in these methods. One effective approach we've identified is diffusion step distillation, which uses a pre-trained diffusion model as a teacher to generate targets through multiple inference steps. We then train a student model to replicate the teacher's output with fewer steps. While previous methods aimed to maintain the generative distribution of the teacher, one-step generation poses significant challenges, as it strays from the iterative denoising process that diffusion models rely on. Although there have been advancements in generating images in one step, achieving high-quality results with fine details and minimal artifacts remains difficult. Video generation has seen even less progress, with early attempts using generative adversarial networks producing low-quality, domain-specific outputs. Recent studies have started to apply image distillation techniques to video diffusion models, but most have focused on small-scale, low-resolution videos. Some concurrent work has attempted to distill larger video models, but they still require multiple diffusion steps. Given the high computational costs of generating high-resolution videos, our goal is to create high-resolution videos in a single step. We introduce a new method for one-step image and video generation that uses a pre-trained diffusion model, specifically the diffusion transformer, as a starting point. We then continue training this model using adversarial training against real data, contrasting with existing methods that use the pre-trained model solely as a teacher. We call our approach adversarial post-training, or APT, as it resembles supervised fine-tuning. Our empirical observations show that APT has two main advantages. It removes the need for pre-computing video samples from the teacher and allows us to exceed the teacher's quality in certain evaluations, particularly in realism and detail. However, direct adversarial training can be unstable, especially with large transformer models. To address this, we implement several key designs to stabilize the training process, including enhancements to the generator and discriminator. Through APT, we have trained one of the largest GANs reported, capable of generating both images and videos in a single evaluation. Our experiments indicate that our model performs comparably to state-of-the-art one-step image generation methods based on visual fidelity, structural integrity, and text alignment. Notably, we are the first to achieve high-resolution video generation in a single step, producing 1280 by 720 pixel videos at 24 frames per second, surpassing previous methods that required multiple steps for lower resolutions. In terms of related work, we note that diffusion step distillation is a common approach to accelerate diffusion models, with existing methods using either deterministic or distributional techniques. Deterministic methods aim to predict the exact output of the teacher with fewer steps but often result in blurry images. Distributional methods focus on approximating the teacher's distribution, but they also face challenges in generating high-quality results in one step. While some methods have been adapted for small-scale video generation, our work stands out as the first to demonstrate one-step generation of high-resolution videos. Section Summary. In this section, we discuss the advancements in diffusion methods for image and video generation, highlighting our novel approach, adversarial post-training, APT, which enables high-resolution video generation in a single step. Our method surpasses previous techniques by directly training on real data, achieving significant improvements in quality and efficiency while stabilizing the training process for large transformer models. Section: One-Step Video Generation. In this section, we explore one-step video generation, which has its roots in generative adversarial networks, or GANs, such as DVD-GAN, MO-COGANHD, DGAN, and Style-GAN-V. These models can create videos with a resolution of up to 1024 pixels, but they are limited to specific types of data, like talking head videos, and their quality is not up to modern standards. More recent efforts, like Animate Diff Lightning and the Motion Consistency Model, have tried to simplify the Animate Diff video diffusion model into a one-step process. They can generate videos at a resolution of 512 by 512 pixels for 16 frames, but they still suffer from noticeable artifacts and reduced quality. In contrast, our method achieves one-step video generation with significantly improved quality and higher resolution. We also discuss stable adversarial training. R1 regularization has proven effective for the convergence of GANs and has been utilized in many previous models to enhance performance. However, recent large-scale adversarial models have either not used R1 at all or have only applied it partially to the discriminator network. This is likely because calculating higher-order gradients is computationally intensive and not well supported by current deep learning frameworks. We propose an approximation method for R1 loss, which we find crucial in preventing training collapse. Our goal is to transform a text-to-video diffusion model into a one-step generator. We accomplish this by fine-tuning the diffusion model using a generative adversarial objective with real data, a process we call adversarial post-training, or APT, as it resembles supervised fine-tuning. We base our method on a pre-trained text-to-video diffusion model that generates both images and videos through a series of diffusion steps. The training involves adversarial optimization, where the discriminator classifies real samples from generated ones, while the generator aims to create samples that deceive the discriminator. We utilize a standard Gaussian distribution for our training data, which consists of paired latent samples and text conditions. The latent and noise samples have specific dimensions related to time, height, width, and channels. We employ a non-saturating variant for our output functions. Our diffusion model is built on the MMDIT architecture and is trained with a flow matching objective using a mix of images and videos at their original resolutions in the latent space. It consists of 36 layers of transformer blocks and has a total of 8 billion parameters. We discovered that direct adversarial training on the diffusion model can lead to collapse. To address this, we first perform deterministic distillation using a mean-squared error loss for simplicity. The distilled model predicts a velocity field from noise samples and text conditions, which we then convert into sample predictions. Although the generated samples may be blurry, this distilled model provides a solid starting point for our adversarial training. We initialize our generator with the weights from this distilled model and focus on one-step generation by always using the final time step. The discriminator is designed to produce a logit that effectively differentiates between real and generated samples. For one-step generation, we need a discriminator with sufficient capacity for stable training. We implement several effective designs to enhance stability and quality, as detailed in our ablation studies. We initialize the discriminator using the pre-trained diffusion network and allow it to operate directly in the latent space, which also consists of 36 layers and 8 billion parameters. Training all parameters without freezing them improves quality, and initializing with the original diffusion model weights yields better results than using the distilled model weights. We also modify the diffusion transformer architecture to generate logits by introducing new cross-attention-only transformer blocks at specific layers. These blocks use a single learnable token to attend to all visual tokens, producing a single output token that is then processed to yield a scalar logit. This multi-layer feature extraction enhances the structure and composition of generated samples. Additionally, we provide the discriminator with raw samples without noise corruptions to avoid introducing artifacts. However, since the discriminator is initialized from the diffusion model, using the initial time step can lead to collapse. Therefore, we propose using an ensemble of different time step values as input, sampling uniformly from the interval and applying a transformation function to adjust the time step. We determine the shifting factor based on the latent dimensions, using specific values for images and videos in our experiments. For efficiency, we sample a single time step for each training sample to compute the necessary outputs. Section Summary. In this section, we discuss our advancements in one-step video generation, highlighting our method's ability to produce higher quality videos compared to previous models, while also addressing the challenges of stable adversarial training through an approximated R1 loss. We detail our approach of fine-tuning a pre-trained text-to-video diffusion model using adversarial optimization, which enhances the generator and discriminator architectures for improved performance. Section Regularized discriminator. In this section, we discuss our regularized discriminator, which has billions of parameters and a strong learning ability but is also at risk of collapsing. To ensure stable training, we utilize R1 regularization, which helps the adversarial training process converge. This technique penalizes the discriminator's gradient on real data, keeping the training aligned with the Nash equilibrium. Implementing R1 requires calculating higher-order gradients, where the first backward pass computes the first-order gradient as the R1 loss, and the second backward pass calculates the second-order gradient for updating the discriminator's parameters. However, at the time of writing, tools like PyTorch FSDP and others do not support this higher-order gradient computation, limiting R1's application in large transformer models. To address this, we propose an approximated R1 loss. We add small Gaussian noise to the real data, encouraging the discriminator to produce similar predictions for both the real and perturbed data. This approach reduces the discriminator's gradient on real data while maintaining a consistent objective with the original R1 regularization. Our final discriminator loss is defined accordingly. In our experiments, we set the parameters to 100 for lambda and 0.01 for sigma for images, and 0.1 for videos. We optimize the generator and discriminator in alternating steps, applying the approximated R1 at each discriminator step. For training details, we start with images at a resolution of 1024 pixels, using 128 to 256 H100 GPS to achieve a batch size of 9062. We set a learning rate of 5 × 10 to the power of -6 for both models. The model quickly adapts to generate sharp images, so we apply an exponential moving average EMMA decay rate of 0.995, adopting the EMMA checkpoint after 350 updates. We then shift to training on videos, which are 1280 by 720 pixels and clipped to 2 seconds at 24 frames per second. We initialize the generator for video training using the EMMA checkpoint from the image stage and reinitialize the discriminator from diffusion weights. We use 1024 H100 GPS to reach a batch size of 2048, lowering the learning rate to 3 × 10 to the power of -6 for stability, training for 300 updates. After just one step of training, we find that the model can perform two-step inference with improved details, although more steps introduce artifacts. We use the RMS prop optimizer with an alpha of 0.9, which is similar to the Atom optimizer but with reduced memory usage. We do not apply weight decay or gradient clipping, and the entire training process is conducted in BF16 mixed precision, using the same datasets as the original diffusion model. In the experimental results section, we validate our proposed adversarial post-training (APT) method. We provide qualitative comparisons of our method against other one-step image generation baselines and analyze the characteristics of the generated images and videos. We also present user studies that quantitatively assess the quality of the outputs. For our baseline comparisons, we select several recent one-step image generation methods, including Flux-Schnell and various SDXL models, as they represent the latest research or are widely available. We compare their original diffusion models against ours using 25 Euler steps, with our model set to a configuration of 7.5. For qualitative evaluation, we first compare the image generation of our APT model in a single step against our original diffusion model using 25 steps. We notice that the diffusion model often produces overexposed images, while the APT model generates images with a more realistic tone. Further comparisons with other one-step methods show that our approach excels in preserving details and structural integrity. For video generation, we compare our APT results with the original diffusion model, highlighting both successful and less successful cases. The APT method improves visual details and realism, although it still falls short in structural integrity and text alignment compared to the original 25-step diffusion model. We invite readers to view the videos on our website for more insights. Section Summary. In this section, we discuss our approach to stabilizing the training of a powerful discriminator using an approximated R1 regularization, which mitigates gradient collapse by perturbing real data with Gaussian noise. We detail our training process for both images and videos, highlighting the effectiveness of our adversarial post-training (APT) method in generating high-quality outputs compared to existing models. Section: Image Generation, 1-Step 25-Step. In this section, we compare our 1-step image generation model to the original diffusion model that uses 25 steps, as shown in the evaluation table. We observe that all 1-step methods show some degradation across 3 evaluation criteria. Our method experiences some decline in structural integrity, but it is better than most existing methods, except for SDXL hyper. While our model is not as strong in text alignment, it still ranks mid-tier in comparison. Notably, we are the only model that achieves a better score in visual fidelity, which aligns with our qualitative analysis that suggests adversarial post-training enhances detail and realism. This improvement over the original diffusion model is due to our approach, which skips using the diffusion model as a teacher and focuses on direct adversarial training with real data. We discuss this further in another section. Next, we compare our 1-step generation to state-of-the-art models in another table. We present both absolute preference scores and adjusted relative changes based on their corresponding diffusion model baselines. The relative preference score helps account for the different quality levels of the base models, calculated as the difference between absolute preference rates and baseline rates. Our results show that our method performs comparably to the best in 1-step image generation, ranking second in absolute preference, just behind Flux-Schnell, and first in relative preference. Our model is favored for its visual fidelity and structural integrity, though it falls short in text alignment, which is a limitation of the APT method. We explore the reasons for the text alignment decline in another section. The relative preference score helps reduce bias from strong base models that could unfairly affect evaluations, and we report base model rates in a separate table. Our base model, which handles both video and image generation, is weaker than dedicated image models like Flux and SD 3.5, and we highlight these differences for clarity in our comparisons. For 1-step video generation, we compare results from 1-step and 2-step methods against the original diffusion baseline using 25 steps. The trend mirrors that of image performance, where our model surpasses the original diffusion model in visual fidelity but shows degradation in structural integrity and text alignment. Despite this, the 1-step generated videos maintain decent quality at a resolution of 1280 by 720. We encourage readers to view the videos on our website. The structural integrity decline is more pronounced in videos due to the added complexity of motion. We consider our work a preliminary proof of concept and stress the need for further research in 1-step video generation. We also find that approximated R1 regularization is essential for stable training. Without it, training collapses quickly. The discriminator loss without R1 regularization drops rapidly, while the loss with it remains more stable. When the discriminator loss nears zero, the generator produces poor quality outputs. In our experiments with the discriminator, we initially thought that using fewer layers would speed up training. However, we discovered that a deeper discriminator with more learning capacity yields better image quality, so we retain all 36 layers of the DIT as trainable parameters. We also verify the effectiveness of using multi-layer features. We find that adding output heads only to the last layer can lead to images with disproportionate structures, likely because last layer features focus more on semantics and less on low-level structures. Using multi-layer features helps alleviate this issue. Lastly, we observe that our model adapts quickly, as shown in our analysis of training iterations. The non-EMMA model generates sharp images even after 50 updates, but the EMMA model generally performs better. We find that the quality peaks at 350 updates for the EMMA model, and extending training beyond this point leads to more structural degradation. Section Summary. In this section, we compare our 1-step image generation method to existing diffusion models and state-of-the-art techniques, finding that while our method shows some degradation in structural integrity and text alignment, it excels in visual fidelity. We also discuss the importance of approximated R1 regularization for stable training, the effectiveness of using a deeper discriminator, and the impact of training iterations on image quality. Section: The effect of the batch size. In this section, we examine the impact of batch size on our model's performance. Our initial experiments indicate that a larger batch size enhances stability and structural integrity for images, aligning with previous studies. For videos, we observe that a smaller batch size of 256 results in mode collapse, while a larger size of 1024 does not. Consequently, we finalize our training with a batch size of 9062 for images and 2048 for videos. Next, we explore the model's internals by freezing it and adding a linear projection to each layer. This projection is trained to align the final layer's predictions using mean-squared error loss, allowing us to visualize the model's workings. Our findings reveal that the shallow layers create core structures, while deeper layers focus on high-frequency details. This process resembles the iterative generation of diffusion models, but in our case, it occurs within 36 transformer layers in a single forward pass. We also investigate the reasons behind visual improvements. Diffusion models lacking classifier-free guidance, CFG, tend to produce poor samples. While CFG is commonly used to enhance perceptual quality and text alignment, it can also distort the generated distribution, leading to synthetic and oversaturated samples. Recent research suggests that the poor performance of diffusion models without CFG may stem from the mean-squared error loss. It has been shown that using perceptual loss can better capture the real data distribution. We propose that adversarial training extends this idea, as it avoids the MSE issue and employs a learnable discriminator that acts as a perceptual critic, helping the generator align more closely with real training data. We then address the causes of structural degradation. By using a one-step image model, we interpolate the input noise to create latent traversal videos. Unlike GAN models with low-dimensional noise, our model operates with high-dimensional noise. We find that interpolating this high-dimensional noise still yields videos with semantic morphing. Our one-step generation model transitions between modes more smoothly than diffusion models, likely due to its shallower depth and lower capacity for drastic changes. We believe that the generator's limited capacity contributes to structural integrity issues, particularly during mode transitions, which can lead to misalignments in text, such as one object appearing as two. The training loss indicates that the discriminator can distinguish outputs before convergence, and we plan to tackle this issue in future work. Finally, we analyze text alignment degradation. Previous studies have shown that diffusion models with CFG can significantly enhance text alignment, sometimes resulting in canonical samples. While adversarial post-training helps align the generated distribution with real data, the real distribution often has poorer text alignment. Our training dataset has utilized recaptions to improve text alignment, so our one-step generation model maintains acceptable alignment, though not as strong as with CFG. We have tested various techniques to enhance text alignment but found them ineffective. These include providing the discriminator with unmatched conditional pairs, which showed minimal improvements in our early experiments, and incorporating clip loss, which negatively affected visual quality. We will continue to explore these issues in future research.